for
We're
those that will be
getting through
following.
it.
And we will start doing the recording soon as well. All right, so we've got a few still coming in. Welcome everyone that has joined so long. Um, we've still got 4 minutes before everyone comes in. Yeah, we're super excited. Thanks for waiting patiently while we were just making sure everything's working perfectly. We are recording and also live streaming on YouTube. So if you do somehow cut out during the webinar, you will be able to re-watch the whole show again. So we'll send that through to you. Okay, I'll let the people in as you guys um, um, speak. We're slowly filling up. The spotlight. There we go. Okay, so we've got quite a mix of people, coaches, runners, physical therapists, um, a whole host of people joining us tonight. All right, so we're just going to give it until past everyone, so just give everyone a chance, and then I'll get us started. You can have that, grab that last cup of tea while we're waiting. Some guy's stuck in the waiting room. This is that awkward silence before we start.
Yeah, it always is, isn't it?
Yeah. Oh no, but it's all right. Okay. I'll keep an eye on the waiting room. All right, I'm going to start the recording. Fantastic. Yeah, apologies for the long questionnaire. I think it's from a previous webinar. I didn't re-edit it, but it's actually great to have all of your information, so that it's nice to get a bit of an idea of where everyone's tuning in from. Hope everyone who's in Cape Town has got a nice warm fireplace going. I've certainly got a nice warm fireplace going in the background. All right. Okay, it's past, so we're gonna kick off, and I'll let people in as we go. I think there might be some that are still filling in the questions, but as I said, also I will also be sharing the recording with everyone who's registered afterwards, and I am currently live streaming on YouTube for those who would prefer to watch through that method. So welcome everybody. Very excited for tonight's topic. It's probably one of the most mentioned words in sports circles. If you were following the Olympics recently, you would have heard the commentators mention the words lactic acid numerous times. But it's also probably one of the most difficult to understand concepts. It's definitely taken myself a long time to get my head around it. And I think it's also one of the most challenging energy systems to know how to apply in training with athletes. And it's also a very difficult energy system I found to explain to people. It's not the easiest question to be asked at a dinner table, explain to me lactic acid. It really is, it takes a while to get your head around it. And that's why I'm super excited to have Prof. Collins, Malcolm Collins, tonight to really take us through. He's a teacher. I've attended of his lectures before, and he's really good at sort of making complicated things simple. So I'm super excited just to have another opportunity to get my head around this energy system. And then Professor Andrew Bosch, who will then take us through some practical applications from a training and racing perspective. I think the greatest thing about Malcolm and Andrew is that even though they are highly accomplished scientists and they will introduce themselves and just share a little bit more about their background, they're also passionate runners. And I think a majority of the people on this call tonight are passionate runners, or they passionate about coaching runners, one of the two. And I think that's what makes me most excited about this talk, is that we're sharing the passion for science and running on this platform tonight, and hopefully there'll be more of this in the future. So I'm going to hand over to Malcolm, and he'll take it away. Just in terms of questions, we definitely will allow as much time as is needed for questions at the end. I've asked him not to talk too long. But sorry, that was just my YouTube live stream coming through. So obviously there's a small delay. So yeah, I ask that if you have questions, maybe type them in the chat, and I'll kind of keep an eye on them as we go through. Because you might have a question that someone else sort of also has the same question, then at least they know the question's out there, if it's in the chat, or you can hold on to it. But yeah, type in the chat, type comments in the chat, and at the end we'll allow time to tackle all of those. All right, so Malcolm, without any how do they always say? Without any further ado, over to you. Malcolm, you must unmute. They're professors, but they still need me.
Yes, I've earned my title by being absent-minded. Oh, so good evening, everybody. Can you hear me now?
Yes, we can.
All right. Coach, thanks again for the invitation to talk to you about this very complicated topic. So as Kathleen has said, my name is Malcolm Collins. I am a professor at the University of Cape Town. Both Andrew and I are within the Division of Physiological Sciences, and we are part of the Health through Physical Activity and Lifestyle and Sports Research Center, which is based at the Sports Science Institute of South Africa. My training is as a medical biochemist, so talking about lactate and how the body produces lactate is part of my basic training. As Coach has said, I'm passionate about running, and I've run many races, road races and trail races in my life, and have the privilege of also being able to do research in the field of exercise science and sports medicine. So with that brief introduction, what Andrew and I are going to do this evening is talk to you about lactic acid and running, and look at the facts, and then try and identify the myths and misconceptions in the field. As indicated, I am a biochemist by training. I'm a basic scientist. And so I'll be doing the first part of the presentation and cover the basics. What is actually happening in your body? And I've tried my best to make it understandable to everybody, recognizing that we probably have quite a diverse a spectrum of people within the audience. And then Andrew afterwards will talk more as an applied exercise physiologist and as a coach himself. What are the practical implications of the basic science, which I'll be covering. So you probably are all aware of some of these misconceptions that are out there in the public domain. And I've just listed 3 of them. The first is that the muscle burn during sprint activities, high intensity exercise, is caused by lactic acid production, which is also referred to as lactic acidosis. I found the following phrase: if you participate in high intensity interval training or similar intense exercise, you probably feel the intense burn in your muscles that often comes with that type of activity. The burn sensation is frequently attributed to lactic acid buildup. A second phrase that often we hear is lactic acid is a waste product that causes muscle fatigue. I found this statement: lactic acid is the waste product produced during aerobic respiration. Running fast can lead to a buildup of lactic acid in your muscles, causing cramp. And then there's a third area which we will not cover this evening, is lactic acid causing delayed onset muscle soreness, or known as DOMS. That's a totally different webinar, and so we will not be addressing that at all this evening. So because we're talking about lactic acid, I need to go back to the basics. And just to remind everybody, what is an acid? And basically, an acid is a molecule that produces a hydrogen ion, and a hydrogen ion, which is an H+, is also known as a proton. And in the slide here, I've got 2 examples of everyday examples of acids. The first is pool acid, and the second is vinegar. So if we think of pool acid, which is hydrochloric acid, and abbreviate HCl, the HCl or the chlorine can give off the hydrogen ion or the proton shown here when you throw your acid into the pool. The second is acetic acid, which is vinegar, and acetic acid shown here can also donate a proton and to produce acetate. And so an acid produces a salt and a proton. And although the structures of acids can vary significantly and can be quite complicated, they all have this ability to donate this proton or this hydrogen ion and to produce a salt as well. So acids, and the reason that this is important is that acids are harmful to the human body. And one of the ways we can measure the concentration of acid in a solution or in our body tissue is through the scale, which is known as pH. And the pH is a scale which runs from 0 to 14, with 7 being neutral. And so those of you who have swimming pools will know that you try and keep your swimming pool at a pH of 7 at neutral. And when you add acid to a solution, or when our bodies produce acid, the pH of the body fluid will drop below 7 towards 0. So the problem is that any buildup of acid within the body is extremely harmful to the body and needs to be controlled. So our bodies are able to maintain our pH at a very narrow range. Blood normally has an average pH of 7.4, but it needs to be controlled in this very narrow range of between 7.35 and 7.45. So any a reaction within the body that produces protons or hydrogen ions will cause this pH to drop below this 7.4 value. And as I said, any accumulation that isn't controlled or dealt with will become harmful to the body and can actually lead to death. So that is the first concept. One of the other concepts that we need to remind you of is that not all muscle is the same. That our bodies consist of two types of skeletal muscle. And I'm specifically saying skeletal muscle because there's also the heart, which is a different type of muscle. And based on the speed at which the muscle contracts, we get fast and slow contracting muscle cells. Now, we're all familiar with this, that if ever we see a chicken, we know that a chicken is divided into the parts of the chicken, which is called the white meat, and the parts of the chicken, which is called the dark meat. The white meat of the chicken is made up of fast contracting muscles, while the dark meat of a chicken is made up of slow contracting muscles. And in humans, we have a mixture of both fast and slow contracting muscle cells within our legs and the other muscles we use to move ourselves and to do activities with. The importance of this is that the fast contracting muscles are used for sprint activities, or what is also known as high intensity activities, while we predominantly use our slow contracting muscles for endurance activities or low intensity activities. And through the rest of this talk, I will be referring to fast and slow contracting muscles and in relation to sprint or endurance activities. So the first message that I need to get across is that muscles, and in particular, it's the fast contracting muscles, do not produce lactic acid. What they produce is lactate. So when we are sprinting or when we are doing high intensity exercises, one of the products of that muscle contraction is lactate and not lactic acid. So why is this the case? To answer the question, I'm going to have to explain the different energy systems used for muscle contraction. And Coach Kathleen mentioned one of them in her introduction, but there are three that our muscles use. The first two are used by our fast contracting muscles during sprint activities or power activities. The first is what is called the immediate energy system. There are other names for it. And this energy system has very limited amounts of fuel within it. And it can only last for a few seconds, 1 or 2, maybe up to about 4 or 5 seconds, sorry. The advantage of this system is that it produces energy immediately. And that is why it is called the immediate energy system. I'll say nothing more about the immediate energy system because there are other energy systems are more important for this topic. The second energy system, which is used by fast contracting muscles, is what is known as the glycolytic, or often referred to as the anaerobic energy system. And it is this energy system that produces lactate. So what is the glycolytic or anaerobic energy system? This energy system uses carbohydrates, and specifically carbohydrates which are stored inside muscle. So the major carbohydrate that we use to drive muscle contraction is glucose. But we do not store glucose in our tissues as glucose, but rather a whole lot of glucose molecules actually link together to form this compound known as glycogen. So the carbohydrate within our fast contracting muscle is stored as granules inside the muscle and known as glycogen. And so glycogen is basically just a whole lot of glucose molecule. So the main fuel for this anaerobic or glycolytic energy system is muscle glycogen. Oxygen is not required for this system, and the importance of that will become obvious hopefully later. There's also only a limited amount of fuel stored in this form within muscle. The energy is released incredibly rapidly as well, but not as fast as the immediate energy system, but it is still very fast. And as I've said, it is the only energy system that produces lactate. It is part of our fight or fright response. That is why it is there. But so that is our second energy system. So within the fast contracting muscles, two energy systems, the immediate, but for the purpose of this talk, is your glycolytic or anaerobic energy system, which uses carbohydrates stored inside the muscle in the form of glycogen, and they produce lactate very rapidly when muscles contract. The third energy system is known as the oxidative or aerobic energy system. Now, scientists and generally we refer to this as a single energy system, but I have divided into two parts, an A and a B. And hopefully the reason for this will become obvious as we progress. And the reason I divided into two parts is because there are two fuels which this system uses. The first is carbohydrates. So glycogen can also is used by this fuel system. And the glycogen is stored within liver and also within muscle itself, but mainly in the muscles that contract slowly. The glycogen here is not converted into lactate, and that I will show the evidence for lately in subsequent slides. So that's the first fuel. The second fuel is fat. And we store a lot of fat in our body, and it's stored in fat cells or adipose tissue or fat tissue. And we are able to totally burn or oxidize both fat and carbohydrates. And therefore, sorry, I'm trying to find my mouse. I don't know. Oxygen is therefore required for this energy system. Most of the energy in our body is stored within the system, and most of it is as fat. About 98% of our fuel reserves are stored as fat. Although there is a lot of carbohydrate, the amount of carbohydrate that we store within our liver and within our slow contracting muscles is nevertheless limited and can become depleted, specifically in endurance exercises over the half marathon or lasting over 2 hours, and Andrew will expand more on that later. Although there is a lot more energy in this system, the speed at which the system is able to produce energy for muscle contraction is much slower than the other two energy systems. And fat, in particular, is slower than carbohydrates. So the total oxidation or the total burning of fat is about 50% slower than that of the total burning or oxidation of carbohydrates. And this is obvious when you see this slide. So what this slide is showing is your track events from your 100 meters down up to your 10,000 meters on the one side, and then your road events from the 5 kilometer to the marathon. On the y-axis, I've got speed in kilometers per hour of the world records for each of these events. And at the top, I've got the pace in meters, minutes per kilometer. The first thing that you can see from the slide is that the world records for the sprint events are much faster than for the endurance events. So if we're taking kilometers per hour, that if you the world record for the 100 and 200-meter sprint events are close to 37 kilometers an hour, where it's just over 20, I think it's about 22 or 23 kilometers an hour for the marathon. And I'm saying this very specifically, that part of the reason, because nothing in biology is that simple, but an important part of the reason why the 100 meters is so much faster than the marathon is because, as indicated in this slide, that for the sprint activity, for the sprint events, you are predominantly using the fuels in your fast contracting muscles, the immediate energy system and the anaerobic or glycolytic energy system. And as mentioned, that these two systems are able to produce energy or drive muscle contraction significantly faster than the oxidative energy system. As we start to rely more and more on the oxidative energy system, you will notice that the world records start to decrease because the production of energy by the systems is much slower, and that is reflected within the world records. So that's the first thing that I want to illustrate. The second thing is that, as mentioned earlier, the immediate and the muscle, the glycolytic energy system only have a very limited amount of fuel within them. And that is why, one of the reasons why they are used for the shorter distances. Once you go beyond 400 meters, one of the reasons is that you slow it down significantly, as you can see from this graph, is because these two energy systems are basically running out of fuel. That is the one reason. The other reason is that although our fast contracting muscles does not produce lactic acid, a proton or a hydrogen ion is produced. And how that is produced, I will explain within subsequent slides. So the cells do become acidic, and to protect those cells from dying, we have to shut this glycolytic system down and go across to your oxidative energy system, which does not produce protons. So the intensity and duration of exercise determines which fuel we use. The faster, the shorter we run, we use our glycolytic and immediate energy systems, but the slower and longer we run, we become more reliant on our oxidative energy systems. I added this slide in a few days ago because it's not you use one system until it runs out and then start using another system. So here is what happened at the Olympics last week for the 10,000 meter finals. And what I've got here is the male winner and the female winner, and their split times for each kilometer, the first kilometer, second kilometer, up to the 10th kilometer, and the pace that they were running each of those kilometers. And if you watched the race, you would have noticed that basically for most of the race, they ran as a bunch at a fairly, well, it looked like a slow pace, although I can't run at 2.5 minutes per kilometer for 9 kilometers. And then they accelerated for the last, it was actually less than a kilometer. Probably, Andrew, if I remember correctly, probably the last 2.5 kilometers. And their fastest kilometer was run in the last kilometer. So in a situation like this, during the first 9 kilometers, they would actually be utilizing their oxidative energy system. Because remember, for the 10,000 meters, most of your energy is coming from the oxidative energy system. And it's only in the last kilometer, probably in the last 400, 800 meters, that they will now accelerate and then start using their fast predominantly using their fast contracting muscles and the glycolytic pathway. So I've mentioned that there are three energy systems. Now, all three of these energy systems are used to produce this molecule ATP, adenosine triphosphate. And ATP is the actual molecule which drives muscle contraction. So your glycolytic pathway, your oxidative pathways are all used by the cell to produce this molecule known as ATP, and it's the breakdown of ATP by the muscle that results in muscle contraction. Now, my next slide is probably the most complicated that I will get as a biochemist. And I've tried to simplify this as best as I can. And for those of you who have done courses in biochemistry, please excuse the oversimplification or the simplification. In this slide, I want to show you that in our fast contracting muscles, we do not produce lactic acid, but rather we produce lactate. In an earlier slide, I mentioned that in our fast contracting muscle cells, one of the fuel systems is known as the glycolytic fuel system and uses this molecule glycogen. And glycogen is built up of glucose molecules. Now, each glucose molecule in this pathway in these muscles, using this pathway, can be very rapidly converted into lactate. So for each glucose molecule, 2 lactate molecules are produced. And it's the salt that is produced, not the acid. There are 12 reactions which are responsible for the conversion of each glucose molecule in glycogen to 2 molecules of lactate. During this process, you will notice that in reaction 4, a proton is produced, and in reaction 7, 2 protons are produced. So in total, 3 protons are produced. However, in reaction 11, 2 protons are used, and in reaction 12, 2 protons are used. So 4 protons are used and 3 are produced. When I went to school, and in fact, I think I've got the maths wrong on the slide. Yes, I do. Oh, sorry, no, it's right. 4 minus 3 is 1, so there is a net use of 1 proton. So this pathway, instead of producing an acid, actually uses a proton and acid in the chemical reactions that take place. The other important thing of this pathway is that it produces ATP. Remember in the previous slide, I said ATP is the main molecule used to drive muscle contraction. So 1 molecule is used here, and 2 is produced here, 2 is produced here, 4 produced minus 1 used. So there's a net production of 3 molecules of ATP. This production of ATP is extremely rapid and therefore is able to drive muscle contraction incredibly quickly, and therefore is the main source of ATP production and ATP use during the sprint activities or high intensity exercise. And as I've said, a proton is actually consumed or used in the production of lactate. And this has been known since the mid-1960s. So where does the proton actually take place? As I said, during sprinting, there is an acid buildup. And this acid buildup actually comes from the breakdown of ATP when the muscles contract. So when the muscles break down the ATP, during contraction, they produce a proton. And it's this proton that causes the muscle cells to become acidic. And what lactate actually does, believe it or not, it delays the buildup of protons within the muscle through various mechanisms, which I will not go into in this presentation. So for those who have done chemistry, this is what I've basically said. The first here is the breakdown of glycogen to lactate, and then how a proton is produced when ATP is broken down. Those are just for those who are interested and have an interest in chemistry. I'm now going to move into the oxidative energy system. This is the energy system that is used during endurance activities. And one of the reasons we use the oxidative energy system during endurance activities is that it prevents the accumulation of protons. So as ATP is broken down and used for muscle contraction, that proton which is produced is used by the oxidative energy system so that there is a net use, that the production cancelled out the use. So there's no acidosis which takes place. We are all familiar with oxidation, the oxidation of carbon. It's a cold evening and some of you are probably sitting by a fire, and there we burn wood or coal. And wood and coal are carbon molecules, and in the presence of oxygen, they will burn, they'd be oxidized, that's what oxidation is, and they produce carbon dioxide and heat. And that heat can be used to cook food or to produce light or warmth. In a similar way, our bodies are able to oxidize carbon compounds. It's not wood, it's not coal, it's carbohydrates, mainly it's glucose or it's fats. These are carbon molecules. And as I said, in endurance activities, the main mechanism that takes place is the oxidation of these two molecules. And when these two molecules are oxidized, some of that released energy is used to make ATP. And that ATP then drives the muscle contraction. There is no proton accumulation during these reactions, and lactate is not produced during these reactions. This is the reason we breathe in oxygen and breathe out carbon dioxide. So again, we're familiar with this concept. In a car, combustion energy, we have a tank, it's a carbon molecule, petrol, we store it, we can fill it up at a petrol tank, and then the engine can burn the fuel in the presence of oxygen to produce carbon dioxide and then release energy to form movement. Our bodies are doing a very similar process. We have a garage, which we can eat food to fill up our fuel tanks, which consists of carbohydrates in the form of glucose. So glycogen in the liver, glycogen in the muscle. So we eat carbs, and they get converted into glycogen in the liver and in our muscle, and that's how it is stored. The fat that we eat gets stored as fat within the fat cells, and excess carbohydrates are stored as fat within the fat cells. When we exercise, our glucose is released from their storage form, and the fats are released from their storage form, used by the muscles, and become totally oxidized to carbon dioxide in the presence of oxygen, and the released energy is used to drive muscle contraction. And of course, we also have fuel pumps and exhausts in our lungs, our heart, and our blood vessels. So there are a lot of similarities there. This slide shows that lactate is not a waste product. That there is limited amounts of carbohydrates that we store within our body. And one of the ways we can spare a carbohydrate, that any produced lactate during a high intensity burst of exercise while running a marathon can then be oxidized by the slow contracting muscle. So lactate is not a waste product, it is a fuel itself and gets metabolized itself. The other important thing, which Andrew will talk about, is because of the limited amount of carbohydrates in our body, especially in exercises over 2 hours, the importance of taking glucose in either orally so that it can have to spare our liver glycogen stores. And I won't talk about this. I'll basically, this is a summary of everything that I've said. I know we're running out of time, but I can make these slides available for those who want to have a look at this. But I do want to end off, and I am nearly finished, is it was interesting to listen to the commentators and the Olympics. And a lot of these commentators need a basic course in physiology and biology. One of the issues at the Paris Olympics, as with a lot of the athletes were complaining about the lack of air conditioners within the village. So what does an air conditioner do? An air conditioner is built to maintain the temperature of a room within a narrow range and the humidity. Our body has a lot of these control mechanisms to maintain certain parameters within a narrow range. Our body temperature, our glucose levels, our pH or hydrogen ion levels, our oxygen content, etc. This concept is known as homeostasis. Unfortunately, I couldn't think of another word to describe it. So there are detectors all over our body which are able to measure body temperature, pH, oxygen levels, blood glucose levels. And if it detects an imbalance, it goes out of the normal range, it'll send a message to a control center, and that control center will then send a message to some effector which says, correct this balance to bring homeostasis back to where it should be. Because any deviation from homeostasis can have devastating effects and harmful effects on us. So what is the relationship between exercise, training, and homeostasis? What exercise does, it disrupts the maintenance of homeostasis. It increases temperature. We require more oxygen. It causes changes in blood sugar levels, etc. And any disruption in homeostasis during exercise will result in fatigue or the perception of fatigue and an inability to maintain that intensity of exercise. So when our world-class athletes were competing at the Olympics and they fell on the ground exhausted after their event, it had nothing to do with lactic acid. It had to do because they are world champions pushing themselves to their limit and they had disrupted homeostasis. Fatigue had set in and they were exhausted, and every control mechanism in their body was saying, stop, so that you can live another day and not cause harm to your body. That is what's happening. Disruption of homeostasis, not lactic acid buildup. So what does training do? Well, training improves our ability to maintain homeostasis. So we are able to control our body temperature for longer. We are able to control our body sugar levels for longer, our pH for longer. That's what training does. So that's one of the benefits of training. It merely delays the disruption of homeostasis. It does not prevent it. Eventually, we will reach a point, even when we are well trained, we are no longer able to maintain homeostasis. So what do we need to do to get back into homeostasis? It's called recovery. Appropriate rest, correct nutrition, allow our bodies to repair. These are the processes that restore homeostasis after exercise. And this is my concluding slide. So what about protons? Muscles do not produce lactic acid. They do produce, these protons are produced during ATP production only during high intensity exercise where muscle glycogen is being used as the main fuel during sprint activities. And this proton accumulation is prevented by the oxidation of carbohydrates and fats during endurance activities in the slow contracting muscles. Lactate is produced by muscle during high intensity exercise. It does not cause fatigue, but it is a marker of fatigue, and Andrew will talk about it. It helps in the delays the buildup of protons in muscle and can be oxidized as a fuel during endurance activities. Why is fatigue important? Well, the maintenance of homeostasis is disrupted during exercise. We can delay the onset of homeostasis, the training, but we can never prevent it. Homeostasis is restored during recovery. Fatigue is a complex physiological process. Anybody that tells you that fatigue is responsible for lactic acid or something else is talking nonsense. Biology is complicated. It is a protective mechanism. So hopefully I've covered the important basic biological mechanisms that happen in your body, and now you can see why we do not produce lactic acid. And I'm going to hand over to Andrew, who will go more into the applied aspects of this topic. Thanks, Andrew. And I'll unshare.
Awesome.
Right.
Thanks, Malcolm. I'm wondering how many people are going to write on their Strava tomorrow, disrupted homeostasis. Uh, so that's gonna be my test. Thanks, Andrew. Over to you. Please, guys, if you've got any questions for Malcolm, type them in the chat so that we can address them. And also for Andrew as he goes. All right, and I'll give over to Andrew.
Okay, Kathy, can you see the screen and everything?
All good. We can see, we can hear, 100%.
Excellent. Thanks, Malcolm. Right, so Malcolm introduced himself and explained where he fits into the university structure and the departments. So I'm not going to go through all that because I'm right there as well. Like him, I've been involved in science for a long time. I've been running for an even longer time, for something like 55 years or so, I think. As a scientist, I've written a number of articles for the popular magazines, Runner's World, and so on, and I'll show you briefly some of that in the near future. And I've also published in scientific journals and on things mostly related to fuel during running and training and so on. At the coaching level, as I moved out of competitive athletics, I wanted to maintain some sort of contact besides my research. So I do a little bit of limited coaching from athletes at the World Championship and Olympic level to those just wanting to finish Ocean's Comrades marathon. And the host tonight, Kathleen, coached her to her PB and the SA marathon title. Remember that? I've been involved in the sub 2-hour marathon project as a co-leader on that project and in charge of the nutrition aspects. I'm chair of the American College of Sports Medicine endurance athlete group and on the committee of the International Ultra Running Association. And when I was younger and faster, had a 2:20 marathon PB and just under 31 minutes for the 10K. So I like to think that I can relate to athletes, and I've, like I said, centered my research around things related to performance and in various ways during my career. Malcolm touched on quite a few angles that I'm going to kind of expand on in a different way. And one of those was, a whole big thrust of his presentation was the myth and misconceptions around lactic acid and lactate and running and so on. And this is one of these things that I find just absolutely amazing in a way, that these myths persist, because the truths have been known for so long. Now, if I can just get my slides to change, yeah. So way in the mid-90s already, I had written an article for Runner's World about lactic acid, labeled "Lactic Acid in Running: Myths, Legends, and Reality." Most runners still believe that lactic acid is released during hard or unaccustomed exercise, and that this is what limits running performance, as well as being the cause of stiffness. Malcolm touched on that as well. Neither is correct, but not even is the terminology of lactic acid. And that was 30 years ago. In the early 2000s, another article in Runner's World that I wrote, which was post-run stiffness, the facts. And there I wrote, lactic acid buildup is the cause of post-hard run stiffness. Wrong. Most runners believe that the stiffness and muscle pain felt after a marathon or hard run is caused by lactic acid. While this was believed correct some decades ago, we now know that lactic acid, or more correctly lactate, is not the cause of stiffness. There were also publications in the scientific press, this one in 1992 already, so a long time back. The effect of training on lactate production and removal. In 2006, also in the scientific literature, misunderstandings about lactate and endurance exercise. And again, in 2007, this one, ventilation and blood lactate in the Journal of Sports Sciences. And so it just kind of continues that we write these articles, but it just doesn't seem to strike with the athletes and those involved in athletics that what they tend to say is wrong. And so here we have, again, Malcolm alluded to things happening in the Olympics, so it's still kind of current. And so Fem Cabal, she was one of the sort of favorites for the 400-meter hurdles title. I say sort of because I expected a good race, but I didn't really expect her to beat the world record holder. Nevertheless, she's a great athlete. She had a very disappointing race and came third. And straight after the race, this is what she said in an interview: all you want to do in an Olympic final is to put up your best race. Well, I think that's true enough. I screwed it up. I just got so much lactic acid with 300 meters to go. This is just a bad race. I'll look at the positives. I'll talk to my coach. I'll try to enjoy the bronze. So I think she is one of those athletes that, you know, you get athletes in third position who are smiling and happy and absolutely ecstatic. I didn't see her in the medal ceremony, but pretty certain she wasn't ecstatic about her bronze medal. Nevertheless, she hasn't got the message about lactic acid. And that's the other, actually even more irritating thing, is how they keep on referring to it as the lactic was building up. They don't even use the right word often as lactic acid. And in this little clip,
hanging on, blowing hard into the straight. The pack are trying to run him down. But Bergen treading water now. The line is coming. Is he going to hang on? Yes, he is. Oh, my word. Drama at the last for Max Bergen. That is what you call trying to run through a sea of lactic acid. It's like running through syrup. We've all been there.
So a sea of lactic acid. Yeah, okay, right. That was the British Championships in the 800 meter event. And again, the commentators during the Olympics just kept on about this lactic acid and lactic and so on. Malcolm showed this slide from the 10,000 meter men's final, and I just wanted to pick up on the pace over here in the last K. So now, if lactic acid is and I'm using that word in the context of this presentation, if lactic acid is really the cause of all that is bad and fatigue and so on, in every single race just about at the top level that is run, and including this one won by Joshua Cheptegei, the last 400 meters was the fastest lap of the race, which he did in 55 seconds. The race averaged out at about 65 seconds per lap, and he did the last lap in 10 seconds faster than that in 55. The guy who came third, Fisher, he was marginally quicker, 54.7. So how do you run your fastest lap when you are full of lactic acid? So, you know, things like just the evidence from what the runners are doing already suggests that we have major problems with this thing, that is lactic acid that is causing all the problems. Now, way back in the 90s already, this is an old slide. So I apologize for that, but I can't reproduce it with modern, better photography. This was a study that was done where we were infusing glucose or lactate, yes, lactate, into exercising cyclists. And if you look at the arm over here where I'm circulating with the pointer, you'll see there's all kinds of lines going into this athlete's, the cyclist's arm. The where this goes to is these so-called infusion pumps over here. You can see these syringes full of, in this case, lactate. And so we infused lactate intravenously, and guess what? Their performance improved exactly the same as if we improved glucose intravenously. So I don't know how that's supposed to happen if the cause of all that is evil is lactate. So what are the determinants of running performance? I'm going to link a couple of things together here, but it'll all come together, I hope, with the theme of tonight of lactates and performance. So some of the key features that determine performance are the one that I'm sure everybody's familiar with, VO2 max. I'm not going to go into it. And then running economy, people might be a little bit less knowledgeable on that. The economy is the amount of oxygen you need to run. And the more economical you are, the less oxygen you need to run at the same speed, or the less oxygen to run a kilometer. Some people have good VO2 maxes and not so good economies. Some have less good VO2 maxes and much better economies. So how do you combine those two? That's in this concept over here of the fractional utilization of max, of VO2 max, which is basically a percentage of VO2 max at which you are running. And I'm pointing this out because I'm going to show you how all this comes together with this guy down here, where we talk about lactate and how it does have a role in determining performance, but not in a bad way. And then just for completeness, muscle fiber type, which I'm not talking about at all. So this is a clip of Paula Radcliffe, who broke the world record for the marathon in 2003 and held that record until not too long ago. And I'm going to just play the clip of the finishing stages of the race because I'm going to be referring to her in the next little while. Whoops, why isn't that play? Just hold on.
Last year she came here, the Athletic fans recognised her. This year she's come here as BBC Sports Personality of the Year, and everybody recognised her. It looks as though, to me, there are even bigger crowds out on the course today, and Paula is receiving tremendous support. She'll really appreciate this as she once again tries to rewrite the standards of women's distance running. I remember Abibi Bikila running 2 hours 15 minutes to win the gold medal in the Rome Olympics in 1960, and Paula Radcliffe is running almost the same time as the great man from Ethiopia did. And just look at the change, just look at how much women's distance running has improved. And the great news for us is this improvement is being led, the record books are being rewritten by Britain's darling Paula Radcliffe.
Into the mall, a huge reception for Paula Radcliffe. They came to see something special from the girl from Bedford, and she's produced it once more. It was a fantastic year last year. World Championships, European Championships, Commonwealth Games, gold medals on the track, a world record in the marathon in Chicago, but they wanted to see her do it in London, and she has produced the goods once more. Never mind, nobody else in the world as quick as her in female athletics. There aren't many men can run faster than this. Paula Radcliffe storming home to win the 2003 London Marathon, Watch the time, watch the clock. She's going to smash the world record. Absolutely incredible. 2 hours, 15 minutes and around 25 seconds.
And that is a time that stood for many, many, many years and only just recently got broken. And that was in the fastest shoes. So she ran 2:15.25 in shoes without the advantage of the carbon fiber plate, which gives you about 2.5 to 3 minutes in the marathon. I'd also must just point out that that time would have been good enough for fifth position. That's fifth position in the men's SA Marathon Champs this year. That's the level of the performance. So what happens to VO2 max as you train? This is oxygen uptake on the left over here, and this is months of training over here. And when you start training, you get quite a rapid increase initially in the VO2 max, but that gradually starts plateauing off. And if we look at Paula's data, and that's why I showed you that little clip, here is the VO2 max on the left, and here's the data for 92 all the way through to when she set the world record at 2003. And what is quite clearly obvious is that she's already on that plateau of around about, for her, 70 mils per kilogram per minute. So that is your upper genetically determined, if you like, level of VO2 max. And I'm going to show you some data just now how with certain types of training that can be improved upon, but not above that genetic ceiling. So what does change? One of the things that changes is, which I mentioned earlier, the running economy. And in Paula's case, here we've got the oxygen uptake over here on the left. And as we move from 1992 through to 2003, you can see how she uses less and less oxygen to run at the same speed. So she is getting more and more economical over the years. And that is one of the things that resulted in her continued improvement in her running, along with changes in lactate. So before I get on to more on that, I just want to combine what I spoke about earlier, the VO2 max values and the running economy values, where it combines into a single value of a percentage of VO2 max. So over here, I just want to show you how, let's just take this running speed of 14 k's an hour. This is the percentage of VO2 max. And in this case, over here, we have a percent VO2 max shown as about 58%, something like that. Over here, this individual is at 50% of VO2 max. So you can draw those lines up together at these different speeds, and you can see that all the way through, in this case here, it could be a second runner, or it could be this runner, as you'll see later, that has improved their percentage of VO2 max. Nevertheless, you can see how as the running speed increases, the percentage of VO2 max is increasing. Now, the marathon is run at 85% of VO2 max, pretty much. So we can draw a line in here, this red line that I've got, and we can then extrapolate these running economies up to that line, and we can then drop down some perpendiculars like that. And what we see then is that over here, with a higher percent VO2 max, it ends up in a running time of about just under 18.75, something like that, kilometers per hour. Whereas the percent max over here, if you extrapolate it up, results in a faster time. So just keep that in mind, because it's going to tie in with something that's going to come up in a little while as I go through the presentation. So lowering the percent VO2 max is a good thing. Right, so skipping forward, we're going to go back to that. Skipping forward to our main topic of the evening, which is blood lactate. Over here, what this shows is how if you increase your running speed, shown at the bottom here, and you gradually get faster and faster, like this shows from 15 k's an hour to 16, 17, 18, and so on, and you measure the blood lactate, there's a slow initial increase in the lactate that we measure in the blood. Now, over here, at this point, just before 19 k's an hour in this depiction, as the person runs faster, there's a sudden increase in the appearance of lactate that we can measure in the blood. And that is called the lactate threshold. It goes under a couple of other names as well, but the most popular one is lactate threshold. And as we train, what happens is this shifts to the right, shown here in the red. So instead of it increasing very rapidly here, after proper training, we can get a rightward shift in this lactate, and the same increase happens at a higher speed than it did before. And that's important because that determines how fast we can run over various distances. And for the marathon, for instance, it happens to coincide with the marathons. The speed at which you can run a marathon is pretty much at this threshold speed. So what determines this? Well, behind the scenes, there's a lot more going on. And that is, oh, sorry, I'm jumping forward. So in the laboratory, we often would take blood samples and spin them down and do proper biochemical assays, etc., to measure the amount of lactate in the blood. But that's been largely replaced now by these simple handheld devices that you can just use a finger prick blood sample to get a blood lactate concentration. They've been proven to be pretty accurate. So going back to that, what determines this point? Well, what's going on behind the scenes is that there's lactate being produced into the blood, and at the same time as lactate is being produced into the blood, there's also mechanisms that are removing that lactate from the blood. So if we look at the solid line over here, and this is the speed at the bottom, as you get faster, there's more and more lactate being produced. But if you look at the dashed line over here, you'll see that the amount of, this is removal, the amount of removal of the lactate almost matches the amount being produced. And that explains this very slow increase that we see over here. But look what happens next. Once we get higher over here, the amount of clearance over here can't keep up with the amount being produced. So somewhat all of a sudden, we get a failure of the amount of clearance. And that explains this sudden increase that we get after this point. So it's an interplay between the amount of production and the amount of clearance. Now, what happens with training? So if this is the point that I've just redrawn over here, this is the point where clearance fails. With more training, what happens is that goes up to a higher point. So that's where it is now in somebody, and after training improves so that the inflection point over here is occurring at a higher speed, resulting in this movement to the right that I showed you earlier. So that's the mechanism behind it. So as Malcolm pointed out, the lactate is not a cause of a problem, but it is a useful tool because it shows us what's happening with other things related to performance and fatigue. And in Paula's data, again, I showed you her VO2 max and her economy data, looking at her blood lactate data. This is the concentration over here. This is running speed again at the bottom here. And if we look at the 92 data over here where my cursor is now, you can see how over the years, it has just shifted more and more to the right, like that. From here through to 2003, where she breaks the world record. Now, some of you might notice that all these curves don't follow that beautiful break point that I was showing you in that previous graph, where there's that sudden inflection. And that's not unusual when we test athletes in the lab. We sometimes can't pick up a nice clean break point. However, that's not too much of a problem, because it just so happens that if you draw a line at the 2 millimolar mark, so that's this particular concentration over here, and there it goes, the point at which it cuts this line over here, the 2003 lactate line, if you want to call it that, that coincides with the speed at which the marathon is run. So if you can find the inflection point, that is most often very close to the speed at which a person can run a marathon. And if you can't find it, you can just draw a curve of from your testing for your lactate, draw the line at 2 millimolar, and you'll pick up pretty much the speed at which one would be able to run a marathon. There are some other ways of doing this, things called the lactate steady state and so on, but this is the most popular method, and lactate steady state is something else, but it's a lot more difficult to measure in the laboratories. It's more time consuming. So this is now, I want to move on to, is just the results of a recent study that I was looking after, where we looked at the effects of training and on the lactate handling and VO2 max economy that I mentioned before, and the fractional utilization or percentage of VO2 max that I mentioned before. Now, in this particular study, we didn't measure lots and lots of points to get a true lactate turn point. We just used five speeds. So you'll see from the graphs to come that we can't and haven't been able to, and never intended to, show a true lactate threshold, but you can see the differences pre and post training. And what the training was in this particular study was we divided runners into two groups, one who continued their normal training for 3 months, and another group where we included a specific type of training called threshold training, which is training done fairly close to the current lactate threshold of the runner. The reason the study ran for 12 weeks is because depending on the level of the runner, it's sometimes necessary to start these people at quite a low number of kilometers on their threshold run, maybe just 3 kilometers, something like that, and then gradually building it up to 8 kilometers. And different runners, as you all will know, adapt at different paces and different speeds, and so some runners needed more time, and so the study ran for the 3-month period. This slide shows some of the initial results of that. On the left-hand side, we have the runners who included the threshold training, and on the right over here, those who continued their normal training. And each one of these depicts an individual athlete. There were 10 in each group, but I'm just showing you a sample of 2 here. This is the lactate on the left. This is running speed over here. It's different speeds for different athletes because everybody is different. And the solid line over here, if we look at this first athlete labeled participant 1, this would be the lactate as we measured at these different speeds prior to the threshold training. And the grayish line at the bottom is at the same speeds after the threshold training. So it's quite clear how at any particular speed, the lactate concentration in blood was lower than prior to training. So we see it here, and we see it here, and every single participant showed the same pattern. Whereas on the right here, these guys continued their normal training, and you can see, looking at the first participant, for instance, in that group, there's virtually no change at all in the lactate curves here. If you look at the bottom over here, in this case, it actually was worse after training instead of better. But what was consistently found, not unexpectedly, was that the lactate handling, as we could call it, over here on the people including the threshold training improved. But interestingly, so did their VO2 max. So this on the left is the group in the experimental group that did the threshold running, and their VO2 max increased. So they hadn't yet reached their genetic potential, unlike the figure that I showed you with Paula Radcliffe. But over here, these guys, over their 3 months of training, they have showed no change in their VO2 maxes. And if we look at the change in running economy, the top line are those runners who included the threshold training sessions, and the line at the bottom in red, they just continued with no threshold, their normal training. And basically this is the different test speeds at the bottom. And what it shows is that the percent change in running economy over here was sitting at about 9%, just looking across like that, whereas it was about 2.5%, 3% in this region over here. So there was a much bigger percentage change, improvement that is, in running economy in these athletes who did the threshold training. Now, going back to what I was showing you before, where we're combining VO2 max with the running economy as a single measure of the percentage of VO2 max with the fractional utilization of max, shown here. Here's our change percent VO2 max. Here's the percentage of change. And in the top group over here, it's the threshold training session group. And if we look at the middle part over here, we're looking at about an 8 to 9% improvement, so to speak. And remember, improvement in percentage of VO2 max here is that the more the higher figure here is better, because they've improved in the percentage of VO2 max more. I'll show you that in the next slide. Whereas these guys here change slightly, but not nearly as much as up here. So what that is showing is they've moved from this blue line, they've improved to this green line over here. So if we go back, it's about an 8 to 9% improvement. And so here we go, for instance, from 70% and an improvement to, in this case, just over 60% as depicted in this figure. So I know it's a bit of a confusing figure, but what has happened here is these guys in red showed a big drop here in the percentage of VO2 max being used at any particular speed. So going through what I did before, that should result in changes of speed. Indeed, that's exactly what we found. And that in a 5K time trial over here, prior to the intervention of the threshold training, this group were just over, they were 21 minutes for their 5K time trial, and they improved by almost 2 minutes post-training, whereas these guys improved very little. There was no significant difference between when they started to when they ended. So how does this get slotted into a training program? The coaches will know that your training pattern should look somewhat like this. If you look down the week from Monday through to Sunday, what has been proven to work very well is you go from easy day, a harder day, easy day, hard day, and so on. And maybe over here, 2 hard days that some athletes can manage, a lot can't. And so you might have 2 easy days here. But then one of these hard sessions, and I've shown it in circled in red over here, that would be the threshold session that I'm talking about. So there's lots of other sessions, of course, that are important as well, besides the threshold session. So I've just shown some of them here. You've got shorter intervals, so that might be your 400 meters and so on the track. Longer intervals going up to mile or 2,000 meter repeats, something called tempo runs, hill repeats, and of course you've got the easy paced longer runs and so on. So when these are added to the training program, the way it should be done is in a slow and progressive manner. You can't just suddenly start including 8-kilometer threshold pace training runs into an athlete's training program. You need to do it slowly and systematically, starting at a much shorter distance and gradually building up. And the maximum that one would do is up to 8Ks. Beyond that, there doesn't seem to be any further benefit. So it's something that's worthwhile to consider including in your training programs. Results in changes in the lactate threshold, moving it to the right, as I described, and at the same time, it allows for some improvement in the VO2 max if you're not already at full VO2 max capacity. It improves running economy, the combination of which allows you to run at any given speed at a lower percentage of VO2 max, and all of that combined results in faster running times. All right, thank you.
Wow, thank you. Sure, I'm definitely going to have to go and watch this all over again. This really is a lot to chew on. What I want to do is allow some time for questions. So you can just raise your hand and we'll let you unmute yourself and yeah, you can fire away if there are any questions from anyone. Perhaps I'll throw one out, which some people might be wondering or not. So Andrew, maybe a practical tip for people on how can they determine sort of that lactate threshold pace sort of without a laboratory?
Yeah, I thought that might come up, but in the interest of time, I didn't include that sort of stuff. So yes, you're quite right. You can come into the laboratory and you can get a proper test done to determine what the threshold is, and then go away and train for a bit and come back again later in a couple of months and redo it and see what the new threshold is. And that's probably the most exact and specific approach. It doesn't have to be like that to be successful. The one thing I would just caution against is don't use your GPS watch. They've got all kinds of funny metrics built in there, which includes measuring VO2 max, and the VO2 max that we measure in the lab never agrees with the VO2 max on the watch, and neither does the lactate threshold. One of the best ways to determine what speed to do your threshold runs at is if you actually race a 15K. Your 15K race pace is a pretty good indicator of a good starting pace for doing these threshold runs. And I say if you're racing it because some runners kind of have one gear only, and they run 10K race the same pace as a 15K race and the same pace as a half marathon and so on. So it doesn't work so well in those cases. But those runners who do have faster time per kilometer for 10 and then compared to 15 and so on. So in other words, they're racing, then your 15K race pace becomes a good indicator. The other way I could think of to determine a plus minus determine a plus minus pace there would be if you take your normal easy run pace and maybe take about 50 seconds per kilometer off of that. So if you normally run 5 minutes a K, your threshold pace would be around somewhere between 4 and 4:10, somewhere in that region. At least as a starting point.
Thank you. We have a question. Do you use 8-kilometer or duration for threshold training? From Elizabeth.
Right. I start a lot lower than that, depending on the level of the athlete. So, as a coach, you would determine where your athlete is at. So maybe somebody can start at 4Ks or 5Ks, and somebody else might have to start at just 3K, something like that. And then gradually building it up over successive weeks from 3Ks to 4 to 5 to 6 to 7 to 8. And as I say, the 8K, all the indications are that you get no further benefit and you're just going to make yourself tired. You can't do a 10K or 12K. Then it starts moving into the realms of tempo-paced runs rather. One of the other training components. So in terms of the threshold run, I draw the limit at 8Ks, and I think most of the scientific evidence base on the studies that have been done support that.
And I suppose for Elizabeth, it would sort of, if she's going in time, it would be sort of progression from 15 minutes, 20 minutes, 25.
Oh, sorry.
Same
I kind of forgot the second part about the time. So thanks for bringing me back to that. So yeah, I do it on distance, not on time. And the reason for that is if you have a half marathon to run, it's 21 Ks, regardless of how slow or fast you are. If you're doing a marathon, it's 42 Ks, regardless of how slow or fast you are. So if you take say a top class runner, they might do their 8K time trial in 24 minutes. And if you have somebody who's going to be racing at 6 minutes a K, if they going to be doing only a 24-minute time trial, they might only do 3 or 4 Ks, and that's not going to be sufficient to have the training impulse that you really want to cause that rightward shift that I was showing in that slide. So do it on distance rather than on time.
Thanks. That clarified that very nicely. Okay, we have a question from Derek. How big is the difference between the threshold pace on my GPS watch and the lab as a rule of thumb? I think that could be a very grey.
Yeah, that's well said. It's very, very grey. I've never looked to see exactly what the relationships are. I just know that it just bears no resemblance. Like for instance, in the study that we've just done that I was describing to you, we tested 20 people and not one was the lab results similar to the watch results. And, it's some were up and some were down. And I think it's like a random number generator. It's the same as when you must have it. You've done a hard morning workout, you do something else in the afternoon, and you sit down to watch TV, and your famous watch tells you, congratulations, your easy day has resulted in better recovery or something. The algorithms built into these things should be reinvestigated.
Elizabeth, but is the slower person not being subjected to a bigger training load, training at the same intensity for longer? I think that could also be viewed.
Yeah. I kind of know where that's coming from. So it's the same as the problem. We can use comrades in this country. That you have the same problem, which I'll explain that now. So I'm going to start with the comrades thing because it'll help illustrate the answer to the debate that you might have about the extra load and so on. So comrades is somewhere around 90 Ks, right? So for an elite athlete doing a 65 or 70 kilometer training run, they're in the shower after just a few hours, really. For the person that's going to be running 10 hours or 11 hours, if they're doing a 65K training run, they are out there for most of the day on their training run. So the question is that training load not too high? Now, it's certainly a lot of time on the legs. So from that point of view, maybe it is high. On the other hand, in terms of absolute speed, I'm not talking now about individual speed, and just in terms of absolute speed, the loading is not as great as our elite runner running at a much faster pace. Every time the elite runner hits the ground, the training, the impact forces are higher because they're running fast and hitting the ground hard. So there's a little bit of balance over there. But the most important thing is that as I said just now, with something else that I was answering, the comrades distance is not going to change. Whether you're going to run it in 5.5 hours or you're going to run it in 11 hours, you still got to get through 90 Ks. So for the person who's going to be on the road and race day for 11 hours, if they only spend 4 hours as their longest training run, they've got a lot of no man's land to get through on race day. So so your slow runner really just needs to get their head around the fact that they need to spend a lot of time on the road. And with this, it's a similar story, that the elite runner who's running the 8K time trial at 3 minutes a K, there are certain loading forces that are going to be higher than the slower runner running it at 5 minutes a K. In terms of the total training impulse, the total training time, yes, it might be a bit higher in the slower runner, but then there's other parts of the physiology. Maybe probably the percentage of VO2 max is a little bit lower. So the person who's done it in 24 minutes, they will be at 95% of VO2 max. The person doing it at 40 minutes will be at a lower percentage of VO2 max. So again, you get a little bit of balance going on. And as I alluded to, it is a debate. At the end of the day, the proof of the pudding is in the eating, and that is that it's the distance that works. And I certainly haven't had people getting injured or overtrained by doing 8Ks if they're a slower runner.
Thanks so much, Andrew. I'm gonna come back to your question because that's going back to the watches again. But I'm not skipping you. We're going to come back to you. I just want to get to this question from Sean because I think running economy, I have a feeling, is something that many would have possibly heard about for the first time this evening. And I remember a German coach. One of the most profound things I learned from him is it's not just about training harder. It's getting to a point where you're running easier, running fast easier, and to me that very much describes running economy. So running fast easier. So Sean Davids asked, share examples of how we can improve our running economy, because I think that's definitely a new word for many.
Okay, so the threshold type session that I've just been talking about is certainly one of them. One of the strengths of this study that I've been talking about here is that there's been plenty of studies done up until now that have looked at different types of training and the impact on certain things. So one study will look at the impact on VO2 max. Another study will look at the impact on economy. Another study will look at the impact on the lactate threshold and 10 point and so on. But this is one of the only studies, believe it or not, that has looked at all of those things in a single training group, in the same lab, everything handled in the same way. So the threshold running certainly improves running economy. We've shown that now, and it's been shown before. The high intensity training, such as short intervals and so on, that has also shown to improve running economy. So there's a number of different training types that improve it. Just time on the road, that improves it too. So just by increasing your weekly training distance. So basically, I suppose what it boils down to is just about any well-constructed training does improve. It does improve or could improve running economy. But right up at the top would be the high-intensity sessions and the threshold runs.
Okay, we're going to go through to back to chart. So we get a measure, for example, new threshold equals, I'm assuming chart that this is your watch telling you this, or something like Training Peaks. New threshold equals 335 at 180 beats per minute. How relevant is the heart rate score?
Okay, again, I'm going to upset the apple cart and say I don't like using heart rate in training. It's so variable. You have all these different training zones and so on, and the whole textbooks have been written on it, and it makes it look like a very exact science. But it's actually not that exact, and very, very little has been done in terms of proper research, to relate heart rate training zones and so on. But there's a couple of important factors to think about when you're thinking about heart rate based training. The one is that so many things influence the heart rate. So if you're a bit stressed, your heart rate's going to be different to when you're more relaxed. The amount of sleep that you've had, the temperature, for instance, affects it hugely. If you're training when it's 28 degrees versus 12 degrees, your heart rate at the same pace is going to be very different. So what is the right heart rate to use? I prefer to base it on proposed race pace. Because once again, that's not going to change. If you need to run your marathon at 4 minutes a K, or you need to run your marathon at 5 minutes a K, whatever it is, that's the pace that you need to target in your training. And if you're basing it on heart rate, it's conceivable that you could end up doing training sessions that are too slow relative to the speed that you're wanting to race at. So, for instance, there's two people that I have where they have particularly high heart rates. If they had to base their training on heart rate in the normal heart rate training zones, they will be absolutely jogging in their training, and they will never have run the marathon times that they've run if they had been based on heart rate.
Thank you. Chart again. Does running form improve running economy enough? Is threshold training a better method? I think, yeah, that's quite easy.
Yeah. So, sorry, just say that again. Does
running form improve running economy enough? So I think he's saying, there will probably some improvements, probably very little. I would think.
I don't know if that's referring to like running style or something.
Yeah. And is threshold training a better method?
That's like mixing apples and pears, I think. But the more you train, the more your style changes to make you more economical. There's been lots of studies that have shown that. So your body is very clever at adapting a style that works best for it. And far be it from a coach to come along and say, oh, you need to change this or you need to change that, and so on. When that has been done, it actually has the reverse effect. The economy often gets worse because Malcolm alluded to it in his presentation, and I'm saying it again now. The body is very clever. It knows what it needs. Give it enough training impulse and it will do the right thing, and more so than what a coach can say. Yes, you can. You look at some of these Kenyan and Ethiopian runners and they look like textbook running style figures. But there's plenty that are far from that. And you could say, oh, he's moving his arm out too far, or his back kick is too much, or he's overstriding. But that's what years and many kilometers of training has produced as being the most effective form. So my message is your training, your running form will become most effective and most economical by just more kilometers run on the road.
So something fascinating, which you
sorry, if I could just add, and of course the threshold sessions as well, because then the adaptation to that from a running form point of view you'll become more economical running fast. For instance, you just have to look at Kipchoge running at 4 minutes a K compared to somebody who's got a marathon time of 5 hours running at 4 minutes a K. They're both running at 4 minutes a K. but they look very different to the ours when you watch them. And partly that is what your questioner was asking, is about form. And so there's a lot of factors. It's body shape, geometry, genetics, length of muscles, joints, leg length, all of it just comes together. So a lot of it you can't change, but the part that you can change is run more, and your body will adapt.
Shucks, I think everyone's getting the bad news that they're going to have to run more. And Elizabeth's got a question again on the threshold. Going back to 8K threshold, is that in one go?
Where's Malcolm's questions?
Broken up into intervals.
Sorry, I missed the question. Just say it again.
So going back to 8 km thresholds, is that in one go or broken up in intervals? If in intervals, break between each.
No, the intervals is a different session. So right at the end there, I had that slide, which I did rush through a little bit because I could see time was marching on. As you well know, there are very many different components that make up a proper training program. And some of those components are intervals, some are thresholds, and then the other sessions that I mentioned, such as hills, tempos, long runs, and so on. So you'll have some short interval sessions that might be 400, 800, even 1,000 meter repeats on the track. And then you'll have longer intervals, maybe mile repeats on the track, 2,000 meter on the track. And then you'll have the threshold run. So the intervals are done with the rest and recovery, but the threshold is one run and one continuous run, and you've got to be careful when you do it as well. It's not to have unintended rest. So you don't want a course that you have to keep on stopping for traffic and so on. And every time you stop, your heart rate comes plummeting down. Going back to heart rate stuff. It's a nice little rest, waiting 30 seconds for the cars to clear, and you do that 2 or 3 times, and you're ruining your threshold session.
Clint's question, I think, is almost a whole nother webinar that I think we need to schedule. What is the rule of thumb around the amount of carbohydrates, electrolytes you would need for a sub 3:30 marathon? My weight is plus minus 65 kilograms. That's a webinar on its own.
That's a webinar on its own. Unfortunately, I really couldn't start trying to answer that. He's welcome to contact me individually. So sorry, whoever, I can't remember, was it Carl? Or
Clint, yeah.
Clint.
That I think needs a consult.
Yeah.
And definitely, Clint, I would advise you. Andrew's is definitely got a lot of expertise on fueling. So it would be worth giving a shout out there. All right, let's take maybe one last question. If there's one last question that someone would like to ask. Otherwise, we're going to call it a day. And I think there's lots for us to go and sit and think about and mull over. Malcolm just explained so well. There's no questions. We're all going to go back and try and re-understand those little diagrams. But definitely a lot to think about. All right, I think that's it for tonight. Guess what everyone's doing for training tomorrow? Oh, there's one more. Okay, as a final question, charts thrown in as the big one, the buzzword that's almost as big a buzzword as lactic acid, double threshold. Does the coaches think double threshold day a good idea? Sure, that's also depending on the athlete a lot as well.
What do you mean by double threshold day?
So it's doing threshold in the morning and doing threshold again in the evening. So closely interspersed, close break between thresholds.
My answer to that is I don't actually know. I've never tried it with an athlete, and I haven't seen anything to look, like a laboratory type study to look at rate of adaptation and so on. My gut feel, having worked with plenty of athletes over the years, as you have, is unless you're an exceptional athlete, you're going to break down. I don't think many athletes would be able to handle 2 high intensity sessions per day. Especially if you think about a lot of athletes sometimes need 2 easy recovery days after a hard session. So if you put a second hard session on the same day, I think it's going to probably spell problems, unless you're a Kiptum or a Kipchoge or something like that. Maybe they can handle it. I mean, from a different perspective, I mean, I've fiddled around over the years with different recoveries after running a marathon, for instance, including running again in the afternoon. And when it comes to recovery, I think, certainly you run your marathon, for instance, and you just need recovery after that. That works the best. And I think when you've done your threshold session, I think you need the recovery after that for the body to adapt to the training impulse that you've just given it. I doubt whether you'd have a major improvement with 2 hard sessions, but I'm not saying it with a good evidence base. I'd be interested to look at whatever data there is to support such a training mechanism. I'm not saying it's not going to work. I'm just saying I'm not familiar with it, and I have my doubts. But if I see good evidence, I'll be quite happy to change my ideas and start introducing it myself. But I won't do it without further good evidence to do it.
Cool, thanks, Andrew. And I think you touched on the one thing which often is not sort of considered with sort of, especially amateur athletes training themselves, is getting that relationship between, as Malcolm says, disturbing the homeostasis and then restoring the homeostasis. So that
exactly.
And that is not so. You've got the great ideas out there like the double thresholds, and I mean evidence of threshold training, but actually bringing it into a cycle of training and getting that relationship between putting in the impulse and then allowing the adaptation. That is where the coach plays a major role. And that in itself, that's another webinar. I think we should be coming up with like a whole year of webinar topics.
Make a list.
Yeah. John will obviously share the recording, etc. So you'll be able to pause and look at the different slides, etc., on the recording, and go over that slowly. So I'm gonna let us all. I'm gonna call it a night. Thank you so much, Andrew and Malcolm. It's been most insightful, and it really, it's given us so much to think about. And thank you. You really explained it in a way that was just so easy to chew and understand. And I think, I think this can maybe just be the start of many more great evenings of education for everyone. So thank you so much for your time. It's massively appreciated.
Yeah, it was great fun. Thanks.
Thanks, everybody.
Thanks, Andrew. Thanks, everybody.
It was great fun.
Bye.
Bye. Good night.
Bye.